particular slide talks about the calculation of heat transfer coefficient, and that is mentioned in section 5.2.4 of ISO 7547/2022. Well, this is very important factor because this formula gives you the heat transfer coefficient of the marine structure. As I already told, that formula is not much of a difference except few couple of additional factors, and you need to understand that it's different than the building sector. As you know, building sector bricks mortars are used, but in marine sector there are no bricks, there are no mortars. What you have is a steel plates and insulation on top of it. So this is very clear. From this you need to understand that it is quite different than the building structure altogether. Now what different it is, that is what we are going to see over here. If you see the formula, it is clearly written and you can note down the formula or you can remember while going for the interview. It is clearly stated here what formula it is, and not only that, there is a calculation also given at the bottom how the value of the heat transfer coefficient is arrived at. That is, AE coefficient of heat transfer surface is wind coefficient, and what are the normal values as per ISO 7547 is also clearly over given here, and more or less it doesn't change. And we have already seen, we are going to see in future what typical heat transfer coefficient you can assume at the earlier stage and to proceed with the calculation unless you go to the EPC stage. So these are some of the formulas which you need to remember and by heart, and you need to apply in your life when you're calculating for the marine oil and gas HVAC installations. So especially this is what the formula we follow, and all values are given over here. You can change that. Suppose the panel thickness is 50 mm, you can just add the 50 mm thickness and you can go ahead. The thermal insulation, whatever it is, you can put the value and you can go ahead. So this is how the example is also given. So you can go through, as a being an engineer, you can easily understand what this example calls for. So you can just go through it and understand what I mean. As I have already explained, the heat transfer coefficient in section 5.2.4, the formula is given, but many of the spaces when you start the work and you don't have the proper value because you have not placed the purchase orders yet, so you have to do the calculation at the beginning. So there are some factors which are already being given by the standard itself, so you can safely use them without any harm. Even if at the later stage this value becomes slightly lower, these are already on conservative slide. So anyway, this value afterwards, even if it becomes lower, it doesn't significantly impact your heat load calculations. So these values you can very safely use, and I will read out each value against what, that is weather deck not exposed to sun radiation and ship inside the external bulkheads is zero point 0.9, which is not exposed to the external bulkhead. You can take as a 0.9 watt per meter square Kelvin. The deck and bulkhead against the engine room and cargo spaces, you can go for zero point 0.8. The deck and the bulkhead, deck is nothing but a roof and bulkhead is nothing but a wall. The deck and bulkhead against the boiler room is 0 0.7. Deck against the open weather deck and exposed to sun radiation and against the hot tank is 0 0.6. Side scuttle rectangular windows 6.5. Side scuttles rectangular window double glazing. Normally double glazing is used, so you can safely go for 3.5. Single glazing nowadays nobody is using. So bulkhead against alleyway, and alleyway and non-sound reducing. Alleyway is nothing but your passage. So you can go for here 2.5. Bulkhead against the alleyway sound reducing is 0.9. You simply go for 2.5 here for the safer side. It doesn't matter, and hardly there is any alleyway which is adjacent to the non-air conditioned area. Normally passage itself is air conditioned, so normally this situation never arises. But still, in case the control room bulkhead ceiling against the engine room is 0 0.8, control room floor against the engine room is 1.2, window triple glazing is 2.5. So these are the values which are given, and you can safely use for your heat load calculation when you have to put the value for the heat transfer coefficient in your HAP or E20 form, whichever it is. So these are the values which you need to use, so you can uh, arrive at these values, arrive at the heat load calculation, one of the important factors. So this is what all about the heat transfer coefficient. The formula is already explained in my previous video. But if you don't have the data for the architecture data, you can safely go for these values. Now let's go for the next slide and see what's inside. Again, this is one of the tables for the ISO 7547 thermal insulance value. It talks about the air gaps and thermal insulance of each of the cases, which is boundaries surfaces of air gaps. So it talks about the surfaces and the respective air gaps, and it gives the value of the air gap thickness. Suppose air gap thickness is 5 mm, the thermal insulance value is this much. So whatever the air gap it is, based on that you can arrive at the values. So this is the purpose of this, and all the if you can see the notes over here, you can clearly see the purpose of these notes over here. So what are these notes, you will understand clearly. So just go through these notes, you will understand the purpose of the aluminum foil and other polished surfaces. As and it's very straightforward, so it is nothing too much to explain. So these values you can use for the thermal insulance for the respective air gaps.